Right, so let's zoom out a little bit and think about what we just did in order to break this monoalphabetic substitution cipher. So the main issue of these simple ciphers is their predictability. The same letter is always encrypted to the same letter, the same word to the same word, and this doesn't mask the frequency of the letters. It just uses a different symbol, and this is what we exploited. So what we did was we found this word that we thought was an encryption of the. Something else you can do, and the is the most frequent three-letter word in English, and that's why we guessed that the most common three-letter word in the encrypted text should be the. However, you can also do this on another level. You can also think about how often each of the letters appear. And if you do that, then that's called frequency analysis. And it's an Arab invention in the 9th century. And actually, the Arabs back then, they studied the like how often letters appeared in different texts, and they did this in order to get closer to God. So originally, this was not invented to break cryptography, but it just turned out that it was applicable also to break ciphers. So the idea is that you take an encrypted text and then you count how often each letter appears. And then you compare that with the distribution of letters in the English language. So if you look across the English language, then you can see that some letters are used much more frequently than others. And if we sort them by which letters are used the most frequently, we see that E is the absolute high score. After E comes T, A, O, I, N. And if we look at our specific text, we saw that the most, well, if we do this for our text, we can see that the most common symbol in the encrypted message was the letter Q, and that indeed was an encrypted E. The second most frequent letter was an E. That was not an encrypted C, that was actually an encrypted O. And the third most was an encrypted N. So we see that, it's not that we can just map the most frequent letter to an E, the second most to a T, the third most to an A. The longer the text is, the more it's going to match, right? So the more the frequency distribution in the encrypted text is going to match English, the longer the text is, of course. So I want to move a little bit because I don't want you to see this line in my face. Maybe over here is better. All right. Okay, and for this particular text, we had a lot of O's. I don't know if you remember, there's a lot of one and stone and mortar and doom. So the text had a little bit more O's than what's normal in English. Right, okay, so just to summarize, how can you build an attack using frequency analysis? Well, what you can do is you can sort the letters of the ciphertext by occurrence, and then you can guess. You can try to replace the most frequent with an E, the second with a T or an A, and then you can try filling in the gaps with some smart thinking. And you keep going on. You can use the frequency list and smart guesses like we did, looking at words and seeing if we could guess which word it was that was encrypted. And if something doesn't work, you of course have to go back and change some of the guesses that you made. So I want you to try this on your own. So you get this text here, and yeah. So I'll pause the video and go try this out. All right. Yeah. And this actually brings us to the end of part 1. And so now I've introduced everything, like almost everything. No, that doesn't bring us to the end of part 1. That brings us to the end of frequency analysis. And now we'll move on to polyalphabetic ciphers. So now you've seen how monoalphabetic substitution ciphers were used for a long time. And the tool to break them was invented in 900 after Christ. 900 after Christ. But of course, it took a while for this tool to spread to every country. So for a while, some countries were able to decrypt the messages of other countries and so on. But eventually it became clear that, we need another encryption tool. One of the tools that was suggested, I mean, of course, there's been many different, right? But one of the ways that you might try to make it harder to break these monoalphabetic substitution ciphers is by changing to polyalphabetic substitution. And the Vigenère cipher is a famous example of this. And it took a long time before that was broken. So the idea in a polyalphabetic substitution cipher is that each plaintext letter is assigned more than one substitute when you do the encryption. So in particular, for the Vigenère, how do you then encrypt? You choose a key or password. It can be any word or sentence. And you translate the key into numbers, and you do that by a letter position in the alphabet. So A is 0, B is 1, Z is 2, and so on. And then when you encrypt each letter of the message, you use different CSAR ciphers. So for the first letter, you encrypt it with a CSAR cipher with a shift equal to the first number of the key. The second letter is encrypted with the CSAR cipher with the shift equal to the second number of the key, and so on. And when you've used all the numbers in the key, then you start over. So let's just see an example. So if we have the keyword Linux, we can translate each of these letters into a shift. And then if you want to encrypt this message, you take your message and put it here, and then first letter of the message is encrypted by shifting it 11 places. So M becomes X. To encrypt A, we shifted 8 places because I is the 8th letter of the alphabet. So that becomes an I. M is then encrypted to Z, A is encrypted to U, A is encrypted to X. So you can see that for this cipher, it's no longer true that each letter is always encrypted to the same letter. So this was a breakthrough that remained secure, I think, for a couple of 100 years before someone figured out how to break this. So of course, but of course it was possible to break. We're not using this anymore. And the way that you go about breaking these Vigenère ciphers, the idea for this is that the key repeats itself. So so the key repeats itself. So the idea to try to break the Vigenère cipher is to first try to identify the length of the key. So you break the message into periodic. So what you do is you try for different lengths of the key. So like try out, okay, maybe the key has length 2, and then you take the message and you break it into sub messages, right? So you collect all the letters that are encrypted with the same key. You collect them in one sub message. So you'll end up, if you guess that the key length is 2, you'll end up with 2 sub messages. And if you guess the key has length 3, you'll end up with 3 sub messages, right? And then each of these sub messages, all the letters there have been encrypted with the same key. And then so therefore you can use frequency analysis to guess what was the shift used, right? So in each of these sub messages, you can then use frequency analysis to try to find E, to try to find out which symbol was E encrypted to. And once you know what E was encrypted to, then you also know the shift of that sublist. So then you can decrypt that entire sublist, and you can do the same for all the sublists. And that should, make it possible for you to break the encryption. Yeah, so that's the idea for breaking Vigenère. Now for the major task of today, you get 2 files. You get both a file that can be broken with that's a simple substitution cipher, and then you also get a text that's encrypted within the Vigenère cipher, and then you get to try to decrypt that one. Right. Yeah. So this text should be analyzed with frequency attack. And then the Vigenère is a longer text. It has to be, right? Because when you break it into these sub messages, then you get less text to work with. So for frequency analysis to work, we need a substantial amount of text. Okay. Yeah. So I'll break this. I'll play some. I'll stop here, I think, and then continue in another video.